Hello and welcome everyone to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today in our second episode of the semester here, we're going to be just kind of introducing physical geography, and then we're going to begin our journey into the great world of mapping. We'll think about geographic grids and just really kind of introduce maps and projections here. And then in the next lecture topic, we will explore that in much greater detail. But first, without further ado, what is physical geography? All right, well, I encourage you at this time, if you will, to pause this radio or video broadcast rather, and define physical geography in your own words, or at least just take a moment to think about it. What is physical geography? Why are we here? Well, coming back to you now, if you're wondering, so you could share your thoughts with your neighbor if you have a neighbor right now, but if you don't, let's see, maybe your ideas of physical geography were similar. So physical geography, by definition, is the spatial analysis. So thinking space and mapping, therefore, that's where we're starting with, of physical components and natural processes of Earth. So we will very much be exploring all of these aspects in much greater detail, including physical components such as incoming energy from the sun, energy dynamics, physical processes on Earth, and then as those physical conditions and processes affect natural biological systems. So as promised, we will be stressing or focusing our attention on interconnections, and all while this component of geography really kind of as the lens where we're thinking about space and change through time and space. So spatial analysis really does help us observe systems on Earth and natural processes, and then think about how they change or maybe don't change so much over space. And we'll also be focusing on time here. All right, so there it is, physical geography, a very brief introduction. So going further with this general introduction of physical geography, we are very much focusing on the four major Earth systems. And so here we'll be focused on the atmosphere, the lithosphere, also known as the geosphere, the hydrosphere, and the biosphere. And I thought right away I could provide some definitions of these major spheres, which maybe perhaps you've heard of before. But I also I thought a pretty nice, fairly short video that I'd like you to check out. I was thinking about integrating it directly into this lecture activity. However, I think it might be a little nicer and literally sound better and look better if you, in fact, check this hyperlink out by yourself, because you'll need to do it for exercise number 1. And so right on Educat, there is an exercises section. Exercise number 1 is currently available for your review and participation, and will require that you do watch said video, which is about 5 minutes long, thinking about Earth and Earth systems and their interactions. So go ahead, check out that video. You can actually just go right to Educat to exercise 1. You can click on the link here, or that video is embedded directly into exercise number 1. So go ahead, check it out. Earth's big idea. Number 3, the Earth's systems interact, and some more visual additions to atmosphere, lithosphere, hydrosphere, and biosphere. That said, and in the meantime, let's go ahead and introduce and define these major Earth spheres. So the atmosphere is a gaseous layer that surrounds Earth. It's essential to life, and it is primarily composed of oxygen, carbon, and nitrogen, among other constituents. All right, there's the formal definition of atmosphere. Moving on now to the lithosphere, which is the solid layer that encompasses the outer 70 kilometers of Earth, including soil and its minerals. All right, So the lithosphere, we'll come back to the lithosphere more specifically later this semester. We will very much be talking about it throughout the entire course, but there will be a dedicated section thinking about geology. And here then now the hydrosphere, water in all forms as it flows and is stored. One of my specialties as a scientist in general. And then the biosphere, the living portion of Earth, including plants and animals, and it is affected by and affects numerous Earth system interactions. So this ES, Earth system interactions. But ultimately, here's the most basic definition of Earth's major spheres. Again, going back just for a moment, make sure to follow through. You could directly click and open this hyperlink through the slide, or simply go to exercise 1 and watch that embedded video and answer the associated questions with essentially this content and the information provided in that video. Okay, moving on now, some of the sub-disciplines, essentially a slide we already kind of looked at in lecture number 1, but just to kind of emphasize, here's the major spheres, the major disciplines associated with these major spheres. So climatology and meteorology, geology, soils, hydrology, ecology, biogeography, etc. I don't ask that you memorize these at this time, but just to kind of give an overview of where we're headed this semester and some of the experiences we'll be looking into. All right, so continuing our very brief and very general introduction to physical geography, it is a science very much focused in process, and as it's in the definition. And so what is a process, at least scientifically speaking? A process is a series of actions that can be measured and that produce a predictable result. And so we'll be focused on some known processes, sequence and series of actions and expectations. If this happens, then what happens? And so that's actually, I think, a pretty fun and applicable part of physical geography. You can simply go for a hike and see something and not just see it, but then understand what would have had to have happened in order for that condition to occur as you see it today. So more on that throughout the entire semester. Okay, systems theory then. So again, system now also in the definition. So process and system, physical geography also being a systems theory scientist providing a holistic, or science providing a holistic framework to analyze or describe how variables work together. Some, kind of science terms there, basically to emphasize again this kind of comprehensive approach or framework to both really measure and analyze certain conditions. Maybe it's atmospheric temperature, maybe it's the velocity of water flow, how fast a rock is tumbling, etc. And then with those measurements and analysis, and then thinking about Earth systems interactions, we can then start to kind of put a sequence or a series of actions to think about how they work together. Okay, so really that concludes our very brief and comprehensive introduction to physical geography. We'll very much be spending the whole semester examining all of these things in much greater detail. But for now, and to really right away this semester set the stage, so to speak, for our spatial understanding of all of this information, we're going to begin with some fairly basic introduction information of geographic grids, and then we'll move into just an introduction to maps. Again, this is kind of a preparation directly here for lecture number 3. All right, so some of this you may have seen in the past at some point in your educational careers, but I thought we'd start somewhere. Oh, it would be so much easier if Earth was flat to measure it and map it. If Earth was only flat. Well, unfortunately, Earth is not flat. It is very much a sphere, or a obloid spheroid, as we'll learn later this semester. It is essentially, for our purposes now, a sphere, and we can then grid or subdivide Earth into different sections. And so how do we subdivide or grid Earth? One of them would be considered a great circle. What is a great circle? It is a circle that bisects equally or Earth equally into halves and passes through, therefore has to pass through the center of Earth, just like perfectly cutting an orange in half here. Essentially, and as we'll learn very soon, all of our lines of longitude are great circles, and then there is only one line of latitude, the equator, that is truly a great circle. Coming shortly here. Stay with me. Okay, so then also in the grid system, we can also then use small circles. What is a small circle? It's essentially any line that subdivides Earth not into equal halves, and so it does not bisect. All right, we do have some pretty well-known small circles, at least in Earth's geographic grid, that some of you have probably heard of, like the Tropic of Cancer and Tropic of Capricorn. The Arctic and Antarctic circles are examples of a geographic small circle grid. Let's now turn our attention specifically to longitude and latitude and think about how they're set up and how they work, as this is fairly basic information, but we need to start somewhere and continue to apply this knowledge in greater detail moving forward. So here we go. Longitude. It determines your location east or west of the prime meridian. So you use lines of longitude to determine your location east or less west than the prime meridian. The lines themselves, as you can see on this image, run north-south. So the line is running north-south, and we actually use it to specifically reference ourselves how many degrees east or how many degrees west of that prime meridian that we're located on Earth's surface. So they run north-south. They are also known as, or synonymous with, meridian. So the term meridian can be used in place of a line of longitude, and the prime meridian itself does in fact run through Greenwich, England. And so here, as this picture shows, here is 0 degrees longitude running right through Greenwich, England here. Perhaps some of you have seen this before. I haven't, but maybe someday I will. So here's 0 degrees longitude, and again, we use it to demarcate or demark our location, determine our location east or west. All right, so a little bit more on longitude, some facts, if you will, the measurement and mapping. And so the greatest distance between a single degree, so 0 degrees and 1 degree east, the greatest distance on Earth's surface is right at the equator. So if you travel from 0 degrees to 1 degree east on the equator, it would be approximately equal to 110 kilometers, or very nearly equal here. However, that distance, because of the shape of Earth, and as you can kind of see, that distance from the equator moving towards the pole just gets smaller and smaller and smaller, where literally every degree of longitude crosses over itself at the north and at the south pole. So effectively there's 0 distance between all degrees. But as you could then kind of appreciate with this image, that distance between a degree of longitude or degrees gets smaller and smaller and smaller as these kind of horizontal black lines are indicate here. Okay, lines of latitude. It determines your location north and south of the equator. So again, we're now using a line of latitude to determine how many degrees north of the equator or how many degrees south of the equator that we are at that place. All right, and then they all run east-west. So in that way, and as you can kind of see on this image, they are all also called parallels. Every line of latitude is literally parallel to one another. So they're called parallels. They run east-west, and you can use them to determine your location north and south of the equator. There's a reason that I repeat things like that as a hint. Okay, a great circle halfway between the north and south poles. The equator is the only line of latitude that is a great circle. And the equator then therefore subdivides or bisects Earth into the northern hemisphere, which we live in, and the southern hemisphere. Unlike a line of longitude, there is a consistent distance between lines of latitude. So every 1 degree latitude, if you go from 0 degrees latitude to 1 degree latitude, you will travel 111 kilometers. If you travel from 89 degrees latitude to 90 degrees latitude at the North Pole, you will also travel 111 kilometers. So that distance between any single degree latitude is the same across all of Earth. And there's the aspect of the parallels also kind of coming to play here. So consistent distance between lines of latitude. All right, where am I? Well, if you look closely at this little X marks the spot, there could be some gold there. There might be somewhere in Marquette. This is in fact the location of Marquette. And so here is the geographic grid as represented with the equator at 0, moving 10, 20, 30, 40, almost to 50, but not quite. So it's over 40 degrees north and less than 50 degrees north. And then going this way, so here's the prime meridian in Greenwich, England, moving to the west. And so we have 10, 20, 30, 40, 50, going further, trying to follow the lines. And we are, as you follow them, not quite to 90. And so there's the 46.5 degrees north, so greater than 40, less than 50. And then here, in fact, we are 87.4 degrees west of the prime meridian. And so that is our latitude here and longitude here of Marquette, Michigan. So some basic information. Perhaps some of you have worked through some of this before at some point in your educational careers. That's about all we need to know right now for latitude and longitude. But again, we're just kind of setting the stage, so to speak, for our more comprehensive understanding of maps and mapping in general. So let's now kind of turn our attention or change it a little bit and think about how currently in the US, our land is subdivided or mapped and gridded. And so this current system that we use in the US was initiated hundreds of years ago, and it is called the US Public Land Survey System, USPLS. And so who were these public land surveyors? Here's a video or a picture of some original public land surveyors, at least creating this grid. Looks like they're hard at work, maybe, or they're just lounging around. Well, anyone know who this person is? Any idea? Well, in fact, that is Douglas Houghton, which is the namesake of the town Houghton to the north of us here, Marquette, in the Keweenaw Peninsula. Douglas Houghton was a public land surveyor and also a geologist, and he is in fact the person who is credited with discovering the copper in the Keweenaw, and so at least making the note of it. I just want to point out that this role as a public land surveyor was likely kind of an interesting challenge, if you will, whereas this picture where they're using survey equipment to run straight lines, it's a pretty open setting. I'm sure it was still challenging, but think about some of the places that these grids and surveys were conducted over rock bluffs and through swamps. And in order to successfully create this public land survey, these surveyors would have had to run lines directly through some of these awkward obstacles. And so what's the point? Why did we go through all this effort and send all of these public land surveyors out into the abyss, if you will, to kind of subdivide the land? Well, the system that was pre-existing, at least in terms of how we occupy and subdivide, buy and sell land and own land in its current form in the US, the pre-existing system was called meets and bounds, and it largely was inherited from the European settlers. And so some of this meet and bound system was pretty squirrely, if you will, for lack of a better word. It was very much not regimented or repeatable, and a lot of it was just kind of written, go to the big tree and take 100 paces to the north, go to the river, follow the river, and then for 300 paces and come back. It might have been a little bit more detailed than that, but there was no kind of set grid system, and so it ended up with lots of disputes and confusion as to what land was whose and how did they line up. And so this was very much more of a systematic way to subdivide here the United States. And so the US Public Land Survey System was the primary way that land is subdivided in the US, and it does use a grid system based upon the cardinal directions, north, east, south, and west. Let's now learn how this system works. Enough about Douglas Houghton and the other public land surveyors. Through this system, and as depicted on this map, over 1.5 billion acres have been surveyed. They largely all start with what are known as the principal meridians. And so here is the Michigan meridian on this map, and here is the fourth principal meridian. The meridians are all named. Some of them have a name like Michigan. Some of them are simply just known as the fourth principal meridian or the fifth principal meridian. And so that's kind of the, at least, starting place for this grid system. So we're going to work through together actually a couple examples, and you should practice and pay attention and perhaps even rewind if you need to, as you will need to apply this knowledge for the second exercise of GC 100 this semester. So how does it work? So again, as I mentioned, first you need to identify that principal meridian and the location at which it crosses a baseline. To kind of go back, there is only one baseline that crosses each principal meridian. And so the Michigan meridian only has one baseline crossing it right there. Similarly, the fourth principal meridian only has one baseline crossing it right there. There's not another baseline. So you always want to start with finding that corner, that intersection between the baseline and that principal meridian. So here's our principal meridian and baseline cross on this kind of set up here, this example. Then you start subdividing into grids, and we're going to start kind of quartering and subdividing into these township ranges and sections. I'm going to walk us through this sequence, and it actually at step 2 goes from most detailed back to coarsest, and we're going to provide a few examples. So if you're not quite visualizing this yet, do not worry, I will walk through it with us all together. And so just to kind of move forward through this system, what they did was they set up these township and range squares, and literally these are 6 miles north by 6 miles east and west. And so each square here, each township and range is 6 square miles. And then each township and range is subdivided into 36 1 square mile sections, as they're known. And so how this works, if you, in this example, we find our principal meridian and our baseline, we're going to go to township 1 north, and then township 2 north, township 3 north, and so on and so forth. So townships always go north or go south. And so we've gone 1 township north of the baseline, 2 townships north of the baseline. So this grade area is 1, 2 townships north of that baseline. And then similarly here, we're going to go range 1 east, range 2 east of that principal meridian. So we've gone 1, 2 ranges, and we've moved to the east of that principal meridian. As it's written in this example, then we're in township T2 north, range R2 east, so R2E. That's our township and range. As I said, within each of these township and ranges, they then subdivided, they being the US Public Land Survey System, into 36 sections. So 1, 2, 3, 4, 5, 6, and it does go in this kind of zigzag pattern for every single township and range. We then would identify here in section 2B the section. So here's kind of this square is now expanded, and now we're looking here at section 25. Okay, and then finally, again, moving forward in this description, you look at its quarter subdivision. So within each of these sections, you can divide it into one quarter. And then if you take that, you could divide that into another quarter, and then the littlest one into the smallest quarter. Anything smaller than the third quarter now gets measured, and it would simply say 150 feet east of this corner. Okay, but in this case, we're not going to take it that far for this class, but just be aware that you can make it smaller, but no longer are they quartered after the third subdivision as it's written. And part of the reason that we're working through this is that if you own or you ever buy or sell property in the US, your written legal description as documented at your local county courthouse and on your deed and on your title, this is exactly the legal description that you're working through. So it is kind of handy to understand this. So here we go. Here's section 25. We can divide here by a quarter, and then here's the second here's the quarter, and then here's another subdivision. So essentially, and I'm going to kind of go slow here. Here's the here's section 25, the major outside square. We cross it once, and now you want to look at this square, and then we cross it again, and now here's this quarter. As written, it always goes smallest to largest. And so in this case, this square that I'm now highlighting is the north and west quarter of, and now I'm going to highlight this square, so that's your second most largest subdivision, of the northeast quarter, and there's only two here, it could go to one more, of section 25 of township 2 north and range 2 east. Okay, so there you go. I just wanted to kind of walk through that as an example here, also in sequence then for you in the lecture is I'm going to walk through that. So first step, identify the principal meridian and baseline. There it is. And then identify your, and in this case, we're right here. So I'm going to go back. Here's our location. I'm showing you on this map that we are right here. Here's that corner, and here's where we're going to be. And so we're going to go north by 1, by 2, and then east by 1 and by 2. And so our township is 2 north and range 2 east, according to this map in our Michigan meridian right here. Now we move in from smallest to largest. And again, this is how the legal description system is set up. 2A is going to be your quadrants as they are known. So your smallest quarter, the northwest 1 quarter of the northeast 1 quarter of the next one. 2B is going to be section 25 here of township 2 north, range 2 east. So they're fully worked through, at least for this singular example, is the Michigan meridian, the lowest quarter subdivision quadrants as here, your section and your township and range. So one more time as an example for a similar setup here, but a slightly different location. First step, identify the principal meridian. Again, here we're going to be now in this shaded region. We're still on the Michigan meridian. So we've identified our principal meridian as the Michigan meridian. We're going to be somewhere in this location identified here. Step 2 then is going to be identifying all of the township range section and then quadrants. However, again, legally, it then goes directly into the smallest quarter subdivision. So I'm going to give you actually 3 subdivisions here. So now look closely at the smallest quarter. I'm in the southwest 1 quarter right here. Now you want to focus on the next largest square, which is right here on your screen. And so this one now is going to be the southeast 1/4. And then your next smallest square is this square. And so this square, your last subdivision, is the northwest 1/4. And so they're written out: southwest 1/4, southeast 1/4, northwest 1/4. Working our way back to sections as highlighted here, you're simply in section 11. And then last but not least, now you'll look through your townships and ranges. Again, your townships go north and south. And so in this case, we are 1 south, 2 south. And so this is going to be township T2S, township 2 south. And then our ranges, again, moving east and west. We're going to look at range 1 east, 2, 3, 4, and range 5 east. So range 5 east, R5E. Okay, if you get confused while you're attempting exercise number 2, I encourage you to repeat and walk through this lecture slide specifically, because your exercise is going to look pretty darn similar to that setup. But now we're moving over to a different meridian, and we have different township and ranges, different section, and different quarter subdivisions. Okay, give that all a shot. Good luck. Let me know if you have questions. With that, I'm going to move on to a few more slides we have remaining in this lecture number 2. So let's think about maps, how they're used, and their projections for a moment. Maps are a primary tool used in geography in general. Most all maps, or any professional map, will have a theme. The one really cool thing I want to mention about maps is it's not just for people like me who love soil and water and rocks and plants and trees and stuff. It's for really everyone. It's for criminal justice, it's for political science, it's for business, all sorts of applications. Think about how many maps you see. Think about watching election cycles and all the maps and the percentages. Again, there's all sorts of applications and uses for maps, and they are in fact used by so many different disciplines and professions across the board. So maps aren't just for physical and natural science. Okay, so there's a theme. This theme are the landforms of the Upper Peninsula of Michigan. Actually, this map produced by Dwight Jerome, who is the soils lab instructor, at least he was this last semester, one of the more knowledgeable soil scientists in the region. And so this is the landforms of the Upper Peninsula of Michigan theme. It has some geographic information, including a scale to know how large or what is the representative scale of that map, and then a legend here depicting these polygons, the colors, which are in fact different type of landforms, mostly deposited by glaciers. Okay, I'm not going to go further into this map. It is one of my favorite maps. Okay, and then here, cartography is a practice, a profession of making professional quality maps. So here you go. You can be a cartographer, and in fact, you could be a cartographer for political scientists or for a news agency or for many other purposes. So just a few more slides here, going into map projections. What is the most complete and accurate way to represent the Earth? How do we map the Earth? What's the most accurate way? Well, it is in fact a globe, which is really useful. However, for a lot of computational purposes and other purposes, you don't always want to just carry a globe around with you everywhere. You need to represent this 3-dimensional Earth on a 2-dimensional surface. How do we do that? And what are the best ways, and are there trade-offs for representing a 3-dimensional Earth on a 2D surface? So most projections, as they're known, this idea of a projection is, again, the fact we're representing 3D Earth on a 2D surface will only preserve one variable, either size or shape, at a time. There are some exceptions, and one of those projections is known as the Goods-Homos line. And this method, this projection, in fact, really does not distort size or shape. However, it is kind of a goofy setup, if you will, for projections. And so you don't often see this in many professional or kind of popular outlets. It is there and can be used. Some more common projections we do commonly see if you use something like maps, your Apple Maps or Google Earth or Google Maps, or on news and other sources. Two major and very common projections we're going to describe here. One is the Mercator projection. The Mercator projection, as it looks like here, maintains correct shape. So the shape of continental features and Earth features are preserved. However, it distorts their relative size. Like, this is not the actual or relative size of Greenland compared to North America and the US here. And so that relative distortion of size is greatest as you move towards the poles. And because there's more landmass here towards the North Pole, there is more, at least observable or visible distortion. So here we go, Mercator, a very common projection. You've probably seen maps both in popular outlets, whether it's on TV or in a magazine that uses the Mercator projection, including other mapping software. So the setup here maintains shape, but distorts size, distortion greatest towards the poles. Moving on, another common projection is known as the Albers projection. And in this case, it accurately portrays size, but in this case, it is distorting shape. And so the shape is most distorted, like Mercator, towards the poles. And so here, kind of the opposite, if you will, or the inverse of Mercator, the Albers now accurately portraying size, but distorting shape. And last but not least is another projection. There are many types of projections, but another common one, and one that likely most of us have seen in some capacity, whether you're aware of it or not, again, through news outlets, popular media, scientific articles, mapping programs, is known as the Robinson projection. This actually is now distorting both size and shape, but trying to do it in a way that's balancing each other out to kind of best represent Earth, the three-dimensional Earth on a 2D space. Oops. And so there you go, the Robinson projection, the last of the ones we'll be talking about, at least specifically this semester, in fact, does distort both size and shape. With that, Dr. VG is signing off.